Welcome to The Explainer. Today, we are diving straight into the absolute fundamental challenge at the heart of, well, basically all research. Whether we're talking about a massive medical breakthrough, a nationwide election poll, or a niche behavioral study, researchers are constantly trying to figure out the truth about a huge group of people. But here's the catch. How on earth do they do that without spending decades and billions of dollars asking every single person? Okay, let's dive into this. Really think about it. If you want to know the prevalence of a specific disease in an entire country, or how teenagers communicate today, examining every single person in that population is literally impossible. We simply don't have the time, the manpower, or the resources to ask everyone. And that right there is the core dilemma that every investigator faces before they collect even a single data point. Here is our roadmap for this explainer. 1. The research dilemma. 2. Probability sampling methods. 3. Non-probability sampling methods. 4. Comparing the two approaches. And 5. Implications for research validity. Let's kick things off with Section 1, the research dilemma. The ultimate solution here is sampling. You take a smaller subset of individuals and you use them to represent the entire population. But, and listen, this is a massive caveat, the sample has to be truly representative. If it isn't, you end up with completely distorted results and statistical biases that can ruin your entire study. The characteristics of your sample, things like age, sex, and health status, absolutely must reflect that broader group you're trying to understand. To get there, the whole universe of sampling basically splits into a giant fork in the road. On one side, you've got non-probability sampling, and on the other, probability sampling. Every single choice a researcher makes branches out from this one critical division. And to understand why picking the right branch is a matter of life and death for a study's credibility, let me give you a real-world example. A while back, investigators wanted to figure out how often adolescents were actually talking to their parents and teachers about AIDS, so they set up what's known as a convenience sample. They just found a group of teenagers who were easily accessible and, crucially, willing to talk to them, and they averaged out the amount of time those teens said they spent talking to adults. Sounds straightforward enough, right? Well, the method they chose drastically warped their reality. Here is the glaring flaw. The teenagers who were bold enough or open enough to talk to random researchers about a highly sensitive topic like AIDS, they were inherently way more communicative than your average teen. By relying on whoever was most convenient, the investigators introduced massive selection bias. They ended up wildly overestimating the amount of communication actually happening out there in the real world. That is exactly how poor sampling completely ruins data. So how do we avoid falling into that exact trap? That brings us to Section 2, probability sampling methods. This approach is built on one absolutely unwavering mathematical rule. Every single element in your population has to have an equal, known, and measurable chance of being selected. Whether a researcher uses systematic, stratified, or cluster sampling, they are always relying on this foundational principle to stamp out the kind of bias we just saw in that teenager study. Let's look at the most basic form, the simple random sample, which is basically the theoretical bedrock for all the complex stuff. It's literally like drawing numbers out of a giant, well-mixed hat. The investigator is essentially shuffling the entire population before blindly grabbing a handful of units. You don't need to examine every member for the exact same reason a doctor doesn't need to drain all your blood just to check your cell count. As long as it's perfectly mixed, a small sample tells you the whole story. But actually, there is a huge catch to this rigorous mathematical path. To put everyone's name in that hat, you literally have to know exactly who everyone is. This means probability sampling requires a complete sampling frame, a comprehensive master list of your entire target population. And let me tell you, creating that list is incredibly expensive, super time-consuming, and honestly, sometimes completely impossible. Which naturally brings us to the other path. Section 3, non-probability sampling methods. When you don't have the time, the budget, or that master list of the population, researchers pivot to these methods. Here, selection relies on the subjective judgment of the researcher, or just plain ease of access, rather than a strictly calculable equal chance. We're talking about convenience, purposive, quota, and snowball sampling. Let's ground this in reality for a second. Imagine you're studying a specific illness. With convenience sampling, you might literally just survey whoever happens to be sitting in a clinic waiting room on a Tuesday morning. It's incredibly fast. It's super cost-effective. However, as we saw earlier, it is highly prone to selection bias. Because, think about it, Tuesday morning patients might have totally different characteristics than weekend patients. But despite the bias, it's a very realistic, practical choice for early exploratory research. And this flexibility is a real game changer for specialized techniques like snowball sampling. This method has massive practical and ethical value. Say you're researching a hidden or marginalized group, or folks with highly sensitive health conditions, like people living with HIV/AIDS or sex workers. There is absolutely no master list to pull from. By having one initial participant recruit another from within their trusted circle, researchers can safely access hidden populations and gather vital, life-saving data.
All right, we've seen both sides. Now for Section 4, comparing the two approaches.
It really boils down to this head-to-head contrast. Probability sampling? It guarantees that equal chance of selection, which keeps bias super low, but it demands that expensive, complete sampling frame. Non-probability sampling. It relies on subjective selection, running a much higher risk of bias, but it completely frees you from needing a full population list, meaning you can deploy it rapidly.
When you weigh them side by side, the real-world trade-offs become incredibly obvious. Look at generalizability. Probability gives you strong external validity, meaning you can confidently apply those findings everywhere. Non-probability? Pretty low on that front. But drop down to resources, and you see the flip side. Probability eats up massive time and money, while non-probability is incredibly efficient. Ultimately, your resources dictate your suitability. You'd use probability for a massive national health survey, but you'd absolutely use non-probability to quietly explore behaviors in a hidden, high-risk group.
And that leads us perfectly to our final so what of the day. Section 5, Implications for Research Validity.
Ultimately, this all hinges on external validity. Probability sampling is still the absolute gold standard if you want to produce hard, generalizable facts. When a study uses it properly, you can trust that its findings actually apply to the broader public. On the flip side, non-probability is unmatched for exploratory insights. It might not hand you a neat national statistic, but it helps you deeply, fundamentally understand why a certain phenomenon is happening in a specific setting. But here's the good news. Modern research doesn't always force you to pick just one side. Today, investigators frequently use mixed methods, giving them the best of both worlds. By combining the approaches, they can leverage the strict quantitative rigor of probability sampling to get those big, reliable numbers, while layering in non-probability techniques to add a rich, qualitative depth. It is a brilliant way to study low-prevalence outcomes because it effectively bumps up your sample size without losing that crucial human context. Which leaves us with this final thought. Every single statistic, every political poll, and every health trend you scroll past in the news, they're all the product of a specific sampling choice. So the next time you see a flashy headline claiming 80% of people believe X, take a beat and ask yourself, did they actually pull names from a well-mixed hat, or did they just ask the people who are most willing to talk? Thanks for joining me for this explainer. Keep asking questions, and I'll catch you next time.